Okay, I'm Lexi, for those of you who do not know. Okay, so we looked at the performance enhancement of college wrestlers through immersive virtual reality training. So we have nothing to disclose. Okay, so historically, looking at the research that has already been kind of like gathered about wrestlers, there's really a lot of focus on the physical factors and the motor functions. And these kind of include the strength, flexibility, aerobic and anaerobic fitness levels. And so when we started to look at ours, we were kind of looking more at the visual side and how that was going to be impacted. So the speed and precision of body movements are clearly important for the wrestlers. And the assessment training of the integrated perceptual motor responses and rapidly changing visual stimuli have not been addressed. So when looking at this, your right side of your brain is more the motor side of everything. It is the one that like executes all your movements. And then the left side of your brain is the side that starts the stimuli and realizes the detection of it. So both of those have to cross paths in your brain. And if those paths are not crossed equally or one is better than the other, there is going to be a deficit. And so we were looking at those deficits through our VR training. So we also had a characteristic, I guess you could call it, of a concussion and head acceleration events, which were proven to be common in wrestling for our research. Failure to identify these impairments and increase the risk for injury. And so immersive reality, virtual reality, provides a means to administer changes to visual cognitive processes that require execution of specific motor responses. And so our purpose statement was to assess the potential value of immersive VR training for actual motor performance enhancement of D1 college wrestlers.
So we collected our data from 24 Division I male college wrestlers. We excluded anyone who either did not complete the pre and post test or they had an injury that prevented them from being able to perform. So for our pre and post test, we did an immersive virtual reality and a whole body reactive agility, which is the tracer. So for the pre and post immersive VR, they had the headset and the hand controllers. They were instructed to begin in a T pose to help decide that field that they would have to reach for. There was a left and right response, and the targets would be in their peripheral vision, so they would have to turn their heads to hit those targets. And the hand controllers provided an auditory or haptic feedback to determine when they had that correct response. So this is what it looked like in the field. You have the two spheres, those are your targets, and once you make that T pose, they go to your peripheral, so you have to find them when the stimulus shows up. So these are the stimuluses. It would either start in the center or on the outside. If it was closed, you would follow the direction of the stimulus. If it's open, you would go in the opposite direction. The metrics that we used to determine their performance or like the timings that they did were perceptual latency and movement time, and combined together made response time. So perceptual latency is that time from when the stimulus appears to when you make that decision to make that movement. So those first few degrees or centimeters of movement is perceptual latency. Movement time is any time after that to when the response is completed, and those together make the full response time. So we had 4 metrics that were measured. That's the eyes, neck, arm, and step. That's for both perceptual latency and response time. And for the composite metric was the rate correct score, which is how fast are they correct, how fast are they getting this right. So then the second part of the pre and post test was the tracer or the whole body reactive agility test. So this was on a monitor instead of in a VR. So it's the same kind of idea where you're in this field and these targets are appearing to your left or your right, and you have to get there and get back as quickly as you can. The total distance to get to the target and back was 1.83 meters. And these are the units that we measured with the tracer. So after the pre-test, we implemented a training program that took place 2 times a week for 3 weeks. It's similar to the actual assessment, except there's no hand controllers. So it's measuring your full body by, instead of reaching with your hand, you're moving into the field with your full body. So there were 2 sets of 20 trials per session, so there's a total of 40. And after that, they did the post test after the 3 weeks of training, and we compared the pre and post using paired synchronicity tests. So we had 5 key findings from these test results. So the first finding was the rate correct score in the perceptual latency. So that is the stimulus, getting the stimulus and making the decision to move. And that's being correct in that decision. So they improved to the point where they were getting an extra correct response every 3 seconds. So they're improving to where they're moving faster and getting more things right. The next was the rate correct score response time. So this is from when they make that decision to actually executing the movement. And they improved where they were getting another correct response around every 7 to 8 seconds. They were moving faster there as well. Our next finding was the arm response time. So this is how fast it actually takes to complete that total movement with the arm. And they improved by 102 milliseconds, which is highly significant. And so this one is the intra-individual variability. So the one before that, you're looking at the mean of all the participants. This one is looking at the 40 trials within one person. So how consistent were they at moving quickly? Were they speeding up, slowing down, or were they going consistently the same? And you can see that they got more consistent after the training. And lastly, this was our tracer finding with the, so earlier we mentioned that it took 1.83 meters to get to the target and get back. So here you can see they started, their total distance was 55 meters for all 20 trials. After the training, they did the tracer again and they decreased their total distance by 5 meters almost. So that was, they were not overshooting as much. They were becoming more precise in hitting those targets and getting back and didn't struggle to find them as much.
Okay, so these are our 4 key findings that we found. So to reiterate kind of what Vic has said is that overall, the rate correct score was the correct response per second. And so this had a speed accuracy balance component. So perceptual latency was the stimulus. So from the time you saw it on the goggles to the initiation of that muscle movement, whether that was turning your head, whether that was taking a step, lunging, however you decided your first movement was going to be. And that had a significant of a P of less than 0.001. The response time for the rate correct score was the stimulus. So that's from the goggles once again to the time that your arm maximally reached the target. And so that was also significant at a P of less than 0.001. And then the arm response time was over the 40 trials, they had a faster response time. And then the trial to trial variability, which was as the cohort as a whole from the time that they did their first trial, since we did the 2 sessions for 3 weeks, then that was more consistent performance overall. And then the whole body reactive agility, total distance, as Vic said before, with the 1.83 meters, they had a greater precision at reaching that target and coming back. So for our discussion, we decreased the IIV of arm responses. And with that being said, it showed that they got more precise within themselves and not necessarily a cohort as a whole, because as we know, everybody has different brain abilities, different steps, we eliminated it best we could, but within themselves, they had a good arm response time. The cognitive, which was the white matter tracks that I was talking about earlier with the cognitive, that is, that is what white matter tracks are, the performance consistency component of the brain. So that goes into the cognitive stability part. The decreased whole body reaction total distance suggests the improvement of visual spatial movement, which was the left side of the brain. And so when both those cross, for our project, we were focused more on the left side of the brain. So our clinical relevance. So as you can see that you have to train both sides of the brain to have any sort of efficiencies to our, it's not all just about the movement and the motor functions that are physically we think of. The brain is also part of the muscles and we need to train those as well. So our project did that. Improvement of spatial visual awareness, is important to increase the movement precision of the wrestlers. So if you think about wrestlers, like their arms and their legs have to have a precision timing to be, they have to be at a precise point at any time, because otherwise they're going to get pinned. Like those little seconds can really make up a huge difference of them winning the match and not winning the match. So if we can, as a whole, as ATs, like kind of go more towards the mental side of stuff instead of just the physical, like ACL injuries or ankle sprains and stuff like that, and really focus on the mental, where that process and lag can be from their brain to their arms and extremities, then we can help them.
Just to kind of add on to this last point, to kind of tie this all together. So you have like there are three things that kind of help with performance. You have the visual stimulus, which is like what we did with the VR of detecting it. You have to detect it, and then you have your cognitives. You have to identify the stimulus and decide which way it's going, and you have to plan that movement. That's what we worked on with this training, is them planning that movement. We worked on the cognitive to help tie together the visual and then the motor, which is execution. So this VR was shown to help that cognitive communication, to help them go from seeing the stimulus and acting on it faster and more precise. Questions?